Okay, welcome to the lesson on significant digits. This is a review from Physics 11. Let's begin. So recall from previous lessons that there are two kinds of numbers. There are exact numbers. There are exactly 12 eggs in a dozen. Most people have exactly 10 fingers and 10 toes. And there are inexact numbers. And any measurement that you do is an inexact number. If I quickly measure the width of a piece of notebook paper, I might get 220 millimeters, which is two significant figures. If I am more precise, I might get 216 millimeters, which is three significant figures. An even more precise measurement would be 215.6 millimeters with four significant figures. The number of digits that are valid for any measurement is called the significant digits. These are the digits that were measured and the final digit that was estimated. The number of significant figures used to express a measurement indicates how precise the measurement was. For example, you have a ruler and there are two arrows on the ruler. The first arrow is somewhere between zero point 0.4 and zero point 0.5. It's not exactly on one of the lines, so you would have to estimate that. You might say it's 0.43 or 0.44. The measurement is an estimate. This arrow, however, is exactly at 1.5. It's right on the line. So it's not being estimated to the nearest tenth of a centimeter. This is being estimated to the nearest tenth of a centimeter. The location of the first arrow is between 0.4 centimeters and 0.5 centimeters. It is at approximately 0.43 centimeters. There are two significant digits. The last digit, the 3, is an estimate. The last digit in any measurement is uncertain. The first zero is not significant because it is just a placeholder. For example, 0.43 centimeters could be written as 4.3 millimeters, where the zero is completely eliminated, or it could be written as 0.043 meters, where an additional zero is added to the beginning. The zero can be removed or another zero can be added without changing the measurement. The digits, the 4 and the 3, have to be there, so they are significant. The location of the second arrow is exactly at 1.5 centimeters. This number would be written as 1.50 to indicate that the 5 is not estimated. The instrument is precise to the nearest tenth of a centimeter. In any measurement, the number of significant figures is critical. The number of significant figures is the number of digits believed to be correct by the person doing the measuring. It includes one estimated digit. The error in a reading is plus minus 1/10 of the smallest division. For example, a meter stick measured to the nearest millimeter is measured to the nearest millimeter, therefore the error any reading is 1/10 of a millimeter, or in other words, the estimate is 1/10 of the millimeter. So for example, 0.2345 meters or 23.45 centimeters, the 5 is estimated. It could be 6 or it could be a 4. Basically, the last digit in any measurement is always the estimate. Zeros can be a problem when determining significant digits. The following rules are used to determine the number of significant digits in a number. Non-zero digits are always significant. All final zeros after the decimal point are significant. So for example, this zero and these two zeros as well as these three zeros are all significant because they are a part of the measurement. They have to be there. But this zero here is not significant because it's only a placeholder that can be eliminated, but these two zeros are significant. Zeros between any other significant digit are always significant. So if you have two non-zero digits, the zeros between them are significant. So this 0 is significant, this 0 and this 0 is not significant. Zeros to the right of a whole number are uncertain. So for example, 2,800 meters or 20 meters or 180 meters, the 0 could be significant or it could not be. It could be an estimate or it could be a measured number. It's not clear when it's written like this. These numbers are usually converted into scientific notation to avoid confusion. The number before the power of 10 is significant. So if this number had 4 significant digits, then it would be written as 2.800 times 10 to the 3. Zeros used to locate a decimal point are not significant. So this 0, and this 0 are not significant. Okay, here's a practice question. Determine the number of significant digits in the following examples. Pause the video now and try it on your own, and then we'll go back over the answers when you get back to the video. Okay, here are the answers. Check your work. If you got any wrong, try to figure out where you made a mistake. If you have questions, then please ask Mr. Johal for help. Okay, adding and subtracting. Operations using significant digits. Rule. The result of any mathematical operation with measurements can only contain one uncertain digit. So for example, if you're adding these three numbers, your answer ends up having three uncertain digits. That's because the 2 is uncertain, so it drops down and becomes uncertain. This 4 is uncertain, so adding 3 to it makes this number uncertain. And this 2 is uncertain. The last digit in each of these numbers is uncertain. So it makes the final answer have 3 uncertain numbers. We can't have 3 uncertain numbers. The rule is the final answer can only have one uncertain digit. So we round this to the nearest hundredth. And the answer becomes 8.04. Another way of thinking about it is that the final answer when you're adding and subtracting can only be as precise as the least precise measurement. So this number is precise to the nearest hundredth, and this one is precise to the nearest thousandth, and this one is precise to the nearest 10,000th. This number is the least precise of all three. So the final answer will get rounded to have the same number of decimal places as this number. So it has 2 decimal places, so the final answer has 2 decimal places. Even though your calculator gives you the answer 8.0372, you must round off to 8.04. Your answer must only contain one doubtful number. Note that the doubtful digits are underlined. Subtraction works the same way. So in this case, you have to round your number in the same manner. Subtraction is interesting when concerned with significant figures. Even though both numbers involved in the subtraction have 5 sig figs, or significant figures, the answer only has 3 significant figures when rounded correctly. Remember, the answer must only have one doubtful digit. So try the following problems on your own. Pause the video now and give it a try on a separate piece of paper. Okay, here are your answers. Check your work and make corrections where you need to. And we're going to go over question 5 in more detail. So here's question 5. When you're adding or subtracting numbers in scientific notation, you have to make the two numbers have the same exponent. So step 1, convert one of the numbers so that both numbers have the same exponent. So we're going to convert 4.2 times 10 to the power of 3, which is equal to 0.42 times 10 to the power of 4. Step 2, subtract the two numbers. 3.34 minus 0.42 is 2.92. And then step 3, insert the exponent. So we put the power of 4 back in. It's 2.92 times 10 to the power of 4. That's your answer. And then the final step is if the final answer is not in proper scientific notation, then change it so that it is. In this case, the final answer is in scientific notation, so we leave it the way it is. And proper scientific notation means you can only have one digit in front of the decimal place. Okay, multiplication and division. The rules for multiplication and division are different than the rules for adding and subtracting. Adding and subtracting is based on precision, and multiplication and division is based on sig figs or significant figures. So rules apply for multiplication and division. Perform the calculation, division or multiplication. Note the factor with the least number of sig figs, and round the final answer to have the same number of significant digits as the second step. So here's an example, 3.22 centimeters times 2.1 centimeters. Step 1, we multiply the numbers and we get 6.762 centimeters squared. Step 2, the factor 2.1 has the least number of sig figs. It has 2 sig figs, and so the final answer has to be rounded so that it will also have 2 sig figs. So 6.762 gets rounded to 6.8. Okay, try the following on your own. Pause the video and then go back over the answers when you get back to the video. Okay, here are the answers. Check your work and make corrections. If you have any questions, raise your hand, ask Mr. Johal, and he'll be happy to help you. Okay, that concludes the presentation. Next, you can work on the practice questions.